Alright, so this is section 10.1, counting principal and permutations. Um, so, let's take a look at the first problem. We'll just sort of work our way through the problems and see what theorems come out of it. So, in the first example, we've got a deli. It's got sandwich combinations, basically, different types of sandwiches you can make up. And so the first thing that you have to choose is a type of bread, and you either get wheat or sourdough, which I'll call W and S. You have three meat choices, and you're supposed to pick one of them: turkey, ham, or roast beef, and two cheeses, so Jack and cheddar. Okay, so we're going to show a tree diagram that shows the different types of sandwiches you get. So, first choice is you're either going to pick wheat or you're going to pick sourdough. Right? And then after you pick wheat, or if you pick wheat, then you're going to break that down into three more choices. You're either going to get turkey, ham, or roast beef. And if you chose the sourdough, you'd have the same three choices: turkey, ham, roast beef. And then after you pick your meat, you pick your cheese. And you either have Jack or cheddar. 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 So each end of the tree here corresponds to one of the sandwiches you could get. You could get wheat with turkey and jack, or you could get wheat, turkey, and cheddar, or you could get wheat, ham, and jack, ham, jack, and so on. And if you count up how many total choices there are, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total choices. So in all, there are 12 different options, different sandwich options, let's say. Now you might be able to tell that really the way you can get this 12 is by saying, well, I first had two choices, and then each of those had three choices, and then after that, each cheese had two choices. And if you multiply 2 times 3 times 2, then you end up with 12. And so the way to think about it is like this. You've got, this will be bread choice. This will be the meat choice. And this will be the cheese choice. And you've got 2 options for bread, 3 options for meat, and 2 options for cheese, and if you multiply that all together, you get 12. This is related to something called the counting principle, so we'll come back to that. Okay, to blood drive, you label blood according to 3 different categories. There's the blood type, which is AB, or O. And then there's something called the RH factor, and you might have, if you've ever donated blood, you might have heard like, oh, I'm A positive or I'm A negative. Well, every one of these has a positive or negative. And then the sex of the donor also goes on the label, so it's either male or female. So how many different labels are there? Well, you could make a tree diagram, A, B, O, and then this goes into positive, and negative, and then that goes into male and female, and male and female, and you could count that up. Or you could do kind of the same thing that we had before. Well, I've got the blood type, right? And then I've got the RH factor. And then I've got the sex of the donor. And each of these has options. I've got 4 possibilities for blood type, A, B, or O. I've got positive or negative for RH factor, so 2 different types. And I've got 2 different types of sex of donor. So if I multiply that together, I get 8 times 2 is 16. So there are 16 possible labels of the blood type. Okay, so let's go on. So in 1 and 2, the idea is that the phrasing of it is that you've got an event that happens. And each event here, like in number 1, the event is making a sandwich. They're composed of smaller events, like picking the bread, picking the meat, picking the cheese, right? So the way that you figure out how many different ways that that event can occur is by breaking it into the sub-events, the smaller events, and multiplying how many ways each of those smaller events can occur. Okay, which is what we just did, right? The main event in number 2 here is labeling the blood, right? And there are 3 mini events to it. There's the event of blood type, the event of Rh factor, and the event of sex of donor. And if you multiply how many different ways each of those mini events can come out, then you get the total number of ways of the main event, the labeling the blood. All right, so let's take a look at 3. So 3 says how many license plates are possible in Texas. It goes 1 letter, then 2 digits, then 3 letters. So 1 letter, and then 2 digits. So digit, digit, and then 3 letters. Letter, letter, letter. Okay, so the idea here is we're going to use the counting principle again. Okay, and you're allowed to repeat letters, so like all of the letters could be A, or it could be A, 2 A's and 2 B's, you know, whatever. So the idea here is, well, how many choices, how many possibilities do I have for the first letter? I've got 26 different possible letters that could go there, A through Z. Okay, how many digits could go in a spot? Well, the digits are 0 through 9. So counting 0, there's 10 total digits that you could use. And then it doesn't matter what digit goes here. I still have 10 possible digits that could go in the second slot, 26 possible letters that could go there, 26 letters that could go there, and 26 possible letters that could go there. One of 26 letters. And it turns out if you multiply all of these things together, you get a massive number. You end up with 45,697,600 possible plates. Okay, now in B, it's a little bit different. You're not allowed to repeat letters or digits. So let's kind of go through this process again. All right, so this one's a letter, this one's a digit, digit, letter, letter, letter. Okay, so first I'll pick a letter. I've got 26 possible choices for that first letter. When I pick the second letter, I'm not allowed to use the same letter that I already used. So I don't actually, you know, if this one's already locked in, I don't really have 26 letters to pick from anymore. I have 25. And then once this one's locked in, I only have 24 letters left that could go there. And then I've only got 23 letters left for the last spot. So something similar happens with the digits. So first I've got 10 choices for the first digit. It could be 0 through 9. But then when I pick the second digit, I'm not allowed to use whatever I used before. So even though there were 10 choices for the first digit, there's really only 9 choices for the second one. And if I multiply all this together, you get 32,209. Whoop, that 2 looks funny. 292,000 plates. So you can tell if you're not allowed to repeat, you drop by 13,000 or so plates. 13 million, sorry. Okay, let's try 4. 4 is related. So you're using 0, 1, 2, 3, and 4 to create 4-digit codes. How many codes are possible if you're allowed to repeat digits? So we've got 4 spots. And in the first spot, you've got 5 possible digits that could go there. And if you're allowed to repeat digits, then you still have 5 possible numbers that could go there, and 5 possible numbers that can go here, and 5 possible numbers that can go there. That's 5 to the 4th, and if you multiply all that out, you get 625 possible codes. What if you can't repeat the digits? Okay, well, by the way, you don't have to keep drawing these boxes if you get the idea. First case, it could be a 0, 1, 2, 3, or 4. Once you've locked that number in, and you're not allowed to use it again, so then there are only 4 numbers left to choose from for the second digit. and then 3 for the next one, and then 2 for the next one. If you multiply that together, you only get 120 possible codes. All right. Let's look at 5. Okay, so 5 has this new symbol that we're talking about called the factorial symbol. And 4 with an exclamation point, you say 4 factorial. And the way you calculate it is you take 4 and then you multiply it by 3, 2, and 1. And you stop when you get to 1. So that's what 4 factorial is. So 5 factorial would be 5 times 4 times 3 times 2 times 1. And you stop at 1, because otherwise you're multiplying by 0 every time. And then you just figure out what that is. That's 20 times 6, that's 120. Now in B, 10 factorial would be terrible to actually calculate. 10 times 9 times 8 times 7 times dot 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 times, let's say, 2 times 1. All over 8 times 7 times dot 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 times 2 times 1. Well, the nice thing about this is that the 8, the 7, dot dot dot, all the way down to the 2 and the 1 cancel with everything on the bottom. You're just left with 10 times 9, which is 90. By the way, if you had to calculate something like, let's say, just 10 factorial for some problem, 10 factorial, that's a pain to do by hand. So on the calculator, let's see if I can call this up. Turns on. You can type in 10 and then go to math and scroll over to where it says probability. So you go to the right and then you go down to number 4. There's factorial right there, and you can hit enter and you can see that's a pretty big number. Okay. Anyway, that's just a tidbit there. Okay, let's take a look at 6. So for 6, you've got a TV news show. It's got 8 stories to present. And in part A, it says, how many different ways can you present the stories? So, well, we've got 8 time slots, essentially. 8 stories to arrange in order. 5, 6, 7, 8. Well, if you think about it, you've got 8 possible stories for the first slot. Then once you've used that story, you're going to throw it away. So you only have 7 stories left for the next slot, and then 6 stories, and then 5, all the way down to 2 and 1. And really what this is this is going to turn into 8 factorial. So if I said I've got n objects and I want to arrange them, and I want to see how many different ways can I put n objects in different orders, it's going to be n factorial. So 8 factorial, well, let's do it on the calculator. It's 8. And then you go to math, scroll over to probability, and go down to factorial. 40,320. That's how many ways we have. Okay, what if there's only time to air 3 stories? Well, let's see. You got 8 ways to do the first story. Could be any one of the 8 stories. Then you've used that one, so then you've got 7 choices left for the next slot. And then you've used that one, so you only have 6 choices left for the third slot. If you multiply those together, 8 times 7 times 6 ends up being 336 different ways of ordering it. Okay, by the way, and this is mentioned down below as well, these orderings here, another way of phrasing this is how many orderings, or the math word is permutations, of 8 objects are there. So I'll just say this. We're looking at permutations of 8 objects. In this one, it's still called permutations of 8 objects because I had 8 original objects. So this is called permutations of 8 objects. Permutations of 8 objects. But in this case, I'm not taking all 8 at once. So you would say instead, taking 3 at a time. So that's how you account for the fact that you're only doing 3. And there's a notation for it. it's actually 8 subscript, the 8 is a subscript, capital P, and then a little 3 right there. Okay? By the way, notice that this right here is the same thing as 8 factorial divided by, and then you need to cancel out the 5 times 4 times 3 times 2 times 1. So over 5 factorial. Right? Okay. Well, actually, so in 7, it says here, an ordering of n objects is a permutation of the objects. There's 6 permutations of the 3 letters A, B, and C. And here are all the different ways you can arrange A, B, and C. We know that if you're trying to permute 3 things, just like up here we're trying to permute all 8 things, if you wanted to permute all 3 things, there are 3 factorial ways of doing it. Well, that's 3 times 2 times 1 equals 6. So that's what this is, right? There's 6 ways to permute all 3 objects. If I said I only want to permute 2 of the 3 letters, how many ways are there to take 3 letters and form 2-letter words? Well, then it would be 3 permute 2. Or it would be 3 times 2. Actually, that would still be 6 ways too. All right. Okay. So let's take a look at what's next. Oh, the 8 permute 3, this thing right here. How can you use that just doing factorial symbols and the numbers 8 and 3? 8, P3. Well, up here we figured out that that's the same thing as 8 factorial over 5 factorial. And that is the same thing as, and we just want to use 8 and 3. Notice it's 8 factorial over 8 minus 3 factorial. So this idea right here is going to give us a blueprint. If you have n objects and you want to permute them taken r at a time, that's going to be n factorial over n minus r factorial. So there's a handy formula if you want to learn that. This is more useful when you have really big numbers that you're dealing with. You have 300 objects and you want to permute them taken 17 at a time. Then this is going to be much more easy to use than actually trying to write it out kind of like this one up here. Okay, so let's take a look. Oh, yes, it was late when I wrote this one. Okay, so let's say you love One Direction. And Zane, which I had no idea was spelled this way till I looked it up, has left, and so you're disappointed in it. And so you decided to make a CD of 5 of your favorite songs, and you've narrowed it down to 12 songs that you could choose. And in this case, it's not just making a CD, it's putting them in an order on the CD too. Just picking 5 randomly to go on the CD and not caring about the order, that's a different type of problem. Here you're taking 12 objects. So you've got 12 objects. And what you want to do is you want to arrange 12 objects, but taking them 5 at a time. Okay. Well, that's 12 permute 5. And you can do this 2 ways. One way is you can say, well, you have 5 slots for the CD, and first you have 12 choices of songs for the first slot, and then once you use that song, you're not going to use it again, so then you got 11 choices for the next one, then 10, then 9, then 8. Or you could use the formula that we had for 12 permute 5, which is going to be 12 factorial over 12 minus 5 factorial, which is 7 factorial. Whoops, on the bottom. Right? You could work that out if you wanted to. ... Or you could work this out if you wanted to. And either way, it's going to come out to be 95,040. Now, there's also a way of doing this on your calculator. Let's see here. I got to find it myself. So I think what I want to do is hit 12 first, but it may be that the calculators have changed since the last time I taught this. Nope, it's the same. So you go to 12, and then if you hit math and scroll over to probability, you can see there's this NPR, right? So I've already hit it. So it's 12 NPR, so 12 is the N. Choose R, or sorry, permute R is the 5. And there's the same answer right there. That's up to you if you want to remember how to do that or not. Okay. So, oh, there are ways to arrange the songs. Okay, let's take a look at 9. Find the value of each expression. All right, now the goal is to do this not just by using the calculator straight up, but actually thinking about what this means. This means I've got 5 objects, and I'm picking 3 of them and arranging them somehow. So how many ways are there that I could possibly do that? Well, if you think about it, I got 5 objects for the first choice, for the first slot, then 4 for the next, then 3 for the next. If you multiply all that out, it's 60. You could also do it by doing 5 factorial over 5 minus 3 factorial, which is 5 factorial over 2 factorial, which is going to be 5 times 4 times 3 times 2 times 1, but then that gets canceled out, so that's still 60 also. Okay, how about 4 objects, and I'm trying to permute them one at a time? Well, if we use the formula, right, you could do a couple things. You could say, well, I got 1 slot and 4 objects that I could fill it with. So that's just 4. You could also think of it as using the formula. You could think of it as 4 factorial over 4 minus 1 factorial, which is 4 factorial over 3 factorial. So that's 4 times 3 times 2 times 1 over 3 times 2 times 1. So those all cancel and you're left with 4 anyway. Okay, in C, we've got 8 objects, and we're permuting them 5 at a time. So this one, I think probably the formula is easiest. You could do 5 blank spots and go 8 times 7 times 6 times 4 times, whatever. Or we could do 8 factorial over 8 minus 5 factorial. So that's 8 factorial over 3 factorial. If you work that out, you're going to end up with 6720. 3 permute 3, well, we've got 3 objects, and we're trying to permute all of them. Well, that's just 3 times 2 times 1. That's really 3 factorial, so that's 6. Or you could go 3 factorial over 3 minus 3 factorial. But that's 3 factorial over 0 factorial. 0 factorial is actually defined as 1. So this is still 3 factorial, which is 6. This here, 0 factorial always equals 1. It's just I think it's just a definitional thing. And then E, 6 permute 0. That's kind of a trick question. So if you have 6 objects and you want to pick none of them and then arrange those, how many ways are there to do that? There's one way of arranging nothing. So if you wanted to use the formula, then it's 6 factorial over 6 minus 0 factorial, which is 6 factorial over itself, which is 1. Right? Okay. So number 10, there are 24 ways to arrange the 4 letters A, B, C, D. And if you think about it, you could get it by just saying to yourself, okay, well, I had 4 choices for my first slot, 3 for the next, 2 for the next, and 1 for the last. And if you multiply all those together, you get 24. What happens if you repeat stuff? If you repeat letters, the C's, like instead of D, let's say they're both C's, right? C and C. Well, then that means that these guys are the same right here. And let's see, what else? These guys are the same right there. And there are some other ones all over the place. C, D. Anywhere that C and D are interchanged, those are going to be the same letter. So every time we're double counting letters, right? So this CD is the same as this one right here, DC, because those would both be C's now. This would be a C and this would be a C, and then it's the same word, right? So it turns out you double count each combination, each permutation that you had. So instead of just 24, it's not 24, but we have to account for the fact that we double counted words that were identical. So there are really only 12 possible words. If it was A, C, C, C instead of A, B, C, D, well, now what happens is it's not just triple counting, it's more than that. So notice here, these would, this word would really be ACCC. And this word would be ACCC, and this word would be ACCC, and this word would be ACCC, and this word would all be ACCC. If you just think of B now as C stays the same, and D is now C also. So it turns out that all 6 of these would really be one word, ACCC. So what it boils down to is we'd have 24 over 6. 4 possible different words. It would be ACCC, CACC, CCAC, and CCCA. Okay, now I'll give you a little tidbit here. The way you actually calculate this, you have 4 objects and you're permuting them, but 2 of them are repeated. So it's actually going to be the ways of permuting all 4 objects divided by the way of permuting the duplicate, right? The ones that are repeated. So in this one, it's really 4 factorial, and then since there are 3 C's, you divide by the ways of arranging the C's, just 3 factorial. That's how you get the 4. Okay. This one's a little bit trickier. This one I've got 4 factorial ways of arranging the 4 letters. And then there are 2 B's, so I have to divide out the 2 factorial ways there are of mixing up the B's, and 2 C's, so you have to divide out the 2 factorial ways of mixing up the C's. So then this comes out to be 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. So these guys cancel, and then I've got 12 over 2, which is 6 ways of doing this one. So that's called permutations with repetition. So the idea here is you've got n objects, like up here is 4 objects, and then one of them's repeated S1 times, so B is repeated twice, and then C is repeated twice, and so on and so forth. So then you would do the total number factorial over the repeated ones factorial, how many times they're each repeated. So we'll try some examples here. How many ways are there to permute the letters in the word cook? Well, there are 4 factorial ways of arranging 4 objects, but these 2 are repeated twice. So you would divide by 2 factorial, and then that ends up being 4 times 3, which is 12. In the next one, we're trying to figure out how many fake words can you get out of Miami? Well, there are 5 factorial ways of arranging 5 objects, and then I've got a double M, so I have to divide by the ways of mixing up the M's. And I also have a double I, so I have to divide by that too. So then I've got 5 times 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1. So these guys cancel, and I'm left with 60 over 2, which is 30. Now the last one, Tallahassee, has 11 letters in it. So there's 11 factorial ways of mixing up those letters. But some of them are repeated. I've got 1, 2, 3 A's, so I have to divide by the ways of mixing up the A's to get rid of the double counting for that. I've got 2 L's. I've got 2 S's. And I've got 2 E's. So then this would be 11 times 10. Well, you know what? These numbers are too big. Let's just go to the calculator. So 11 factorial, whoops, wrong one, math probability factorial divided by 3 factorial times 2 factorial is just 2 times 2 times 2. 831,600 ways of arranging those letters. All right, I hope that helps a little bit.